All right, everybody. So welcome to week 10. Hopefully, and I apologize for the video here. I guess it's not that important that you see my face. If it is, we'll turn the lights on. But anyway, I hope the midterm went okay. I'm willing to answer any questions on that. I can sort of do it live in lecture now, or I haven't really seen any. Well, too many specific questions about the midterm, but anything before we get into the lecture?
When does it close?
Well, so let me review the protocol on due dates and all that. So the question was, when did the midterm close? And I'll just review the due date policy for this course and the other courses I teach briefly, so we're all on that same page. So here is the course, Recycling Technology, and we're into week 10 now. I don't have anything listed yet because I haven't made any recordings. Well, I'm working on that as we speak. But for each week, for example, week 1, the week 1 quiz was launched on Thursday of week 1, and you are to finish that before the Tuesday of week 2. And so the same thing is true with the midterm. I launched that on Thursday of week 9, and so it was due as of 40 minutes or 20 minutes ago. It's due before lecture starts the following week, so that we can review it in class and everyone is on the same page. So the midterm is officially overdue since it was launched Thursday of last week. You had 5 days to take it, more or less. So it's now overdue. If you need an extension on that, just email me. So okay, so plastics. What I want to cover today is more or less the toxicity of PVC. So just a second ago, I overheard a conversation about plastics becoming toxic in the landfill. Now let's review plastics in general. So, and to do that, we need to look at the chemical structure. So I'm going to just look up LDPE and HDPE. And I'm just going to do a little bit of web browsing, and then we're going to dive into the deeper epidemiological data on some other plastics. But I'm just going to say, for the sake of argument, I could eat a plastic bag. Like I could eat a low-density polyethylene plastic bag or a high-density polyethylene plastic bag and not get sick, assuming there's no mechanical blockage, because there's nothing in here that's well, toxic. And we can take a look at it. But let's look at the chemistry. Again, I'm just going to kick around a little bit here. So high-density polyethylene. Before we go too into that, let's just look up ethylene. And ethylene really could not be a simpler molecule. It's just sort of one level more complex than methane. Methane's 1 carbon and 4 hydrogens. Ethylene is 2 carbons and 4 hydrogens. You wouldn't want to breathe it necessarily, but once it is in polymerized solid form, there's nothing toxic about it, and that's why we use it in all of our packaging.
Well, what is it usually, a 1, a 2?
Oh, we'll get into what that is briefly. I'm just looking at the ethylene molecule itself, because this is the backbone for 2s and 4s. LDPE is 2, HDPE is 4. But this is the molecule ethylene. And what I'd like to look up is its melting point. So it's it's a gas. As you can see here, that it's boiling more or less at negative 104 Celsius. So anything above that temperature, ethylene is a gas. Just like propane is a gas, butane is a gas, etc. Methane is also a gas. So ethylene itself is a gas. You wouldn't want to breathe it, but once it's polymerized, let's look at polyethylene. And so there's your ethylene monomer, your 2 carbons, and after that you've just sort of knocked off the 2 hydrogens and made this long chain. So this is the monomer, and let's take a look at the polymerization. Okay. Ethylene, as we probably guess, is a stable molecule, polymerizes only upon contact with catalysts. The conversion is exothermic, meaning it gives off heat. Coordination polymerization, the most pervasive technology, it means the metal chlorides or metal oxides are used. So the chemical process itself is going to be relatively toxic. Anytime you've got titanium chloride, et cetera, et cetera. There's chromium involved. So once you've done the polymerization with these various steps, now we're looking at density and branching. So let's look at high density polyethylene. So it's your HDPE, that's your number 4. Oh, I'm sorry. Yeah, it is. 4 is low density. 2 is high density. Thank you. Yeah, HDPE is number 2. Here's something that's important to note. The density of most of these plastics is right around that of water. In fact, it's a little bit less than water. Is that a good thing? Is it a bad thing? Well, in some sense, it's good for an industrial process where you actually want to separate plastics. It's bad in the sense that it's kind of floating out there in the ocean at about neutral buoyancy and being ingested by marine life. Let's see if we can't. I want to get a nice. I want to get a nice image on the HDPE molecule. So molecularly, it's relatively boring. It's just repeating carbons and hydrogens. And what we can see here, let's take a look at this guy. Yeah. So HDPE, it's just a bunch of really long chains of this ethylene right next to each other. The lower densities have these little side branches. And so it's just not, the LDPEs are not as stiff, they're not as strong because they don't have, and maybe I will use a little bit of finger puppets, they just don't have as much shear interactions. So imagine a nice long rope with nice long fibers. All of the fibers are touching each other and have very good tensile properties, difficult to pull apart. but in a branch chain, everything's sort of, mangled and tangled and much stretchier, less stiff, and not as strong. So that's, at the molecular level, that's the difference between HDPE and LDPE. Okay. I've also talked a little bit about international biomass, and this is why I just want to make a little plug for some of the waste to energy topics that we've been talking about. International Biomass Pellet. Find these guys in so this is Patrick Brown here in town. He's done a pretty good job with some of his fundraising. And the product that they have, and I'm hoping to find an actual image of this guy. Oh, here we go. This is a good shot of it. And it's and you've all seen the wood stove pellets, and they're, and that's more or less what this guy is. The international biomass pellet is bigger. So whereas the wood stove pellet's maybe as big as your pinky, the international biomass pellet more sort of cigar shaped, maybe an inch in diameter, and it's got this high density polyethylene embedded with it. It's mostly wood, but with the high density polyethylene embedded with the wood, it's now a waterproof plastic or a waterproof pellet in a very similar sense to how coal is. So coal is shipped internationally. Coal is also hydrophobic, relatively low water content. These guys repel water. They can be stored outdoors and used as a waste energy product. So we've already talked about cellulose. Here you're kind of getting the best of both worlds. You've got the energy of the cellulose, of the woody biomass, and the energy of the polyethylene. As we just saw, it's just carbon and hydrogen. There's no mercury in it, like you might see in coal. There's no sulfur in it, like you might see in coal. There's no other heavy metals. So in terms of a combustion product, it's going to be cleaner. And in terms of the chemistry for burning this in a power plant, that's exactly what it's designed to do. The effluent is much cleaner. It's just going to be pure CO2 that can be sent into an algae pond, et cetera. So I'm really looking at number 2s and number 4s as a fantastic waste to energy process. And you might expect to see something like this on the final again, because if you did the midterm, you saw that sort of break-even point for aluminum. What's it really cost me? How many cans do I need to collect before I fire up the jalopy and drive them out to Axman? Same thing here. How much plastic and wood do I really need in one place at one time to be competitive with coal? So, all right. So we've talked a little bit about the density of HDPE. We've talked a little bit about tensile strength, knowing that the reason that HDPE is stronger than low-density polyethylene is, again, because of those shear interactions among the longer molecules within the plastic. We've also talked about its chemistry, and we know it's just plain old carbon and hydrogen, and it comes from ethylene, which is initially a gas. Okay. So any questions at all on 2s and 4s? I'm gonna save Thursday for Eddie Stan to talk a little about more of some of the other ones, the 1s, the 3s, the 5s, the 6s, the others. But these are, pretty basic, pretty simple. We make a lot of it, and I think the best use for them at the end of the day is a waste to energy pathway. And you can make arguments to the contrary. In fact, I would welcome suggestions where you're getting the most economic bang for your buck. So maybe, hey, don't turn that into a energetic product. Turn it into a building product instead. It's got to go somewhere. So, all right.
Where's the woody biomass come from?
Oh, great question. So in International Biomass's strategy, what they're really looking to do is they're looking to get it from here. So you've got this beetle kill, and there are private landowners who have sufficient capital to pay a forester to come in and remove these materials so that their house doesn't burn down. Unfortunately, our federal policy is such that we don't preemptively go in and mitigate fire hazards. Because a lot of times you get a lot of environmental back and forth about someone saying, oh, no, just leave nature as is, don't go touch it. The problem is you get so much dead fuel backed up, piled up, stockpiled, what have you.
It doesn't become a surface cleansing.
No, exactly. Instead of sort of this cleansing fire, you get these giant fires that more or less turn the landscape into the surface of the moon. So I actually sat down at the Department of Energy last week, talked a little bit about, to some of the fossil fuel guys about using this, product, International Biomass's product, as a, I don't like to use the word alternative, but as a sustainable substitute for fossil fuels, because it's sitting right there. It's not like, if it's going to burn, it's when it's going to burn. And I think we've got enough satellite data coming out of Steve Running's shop to say, we know where the fires have happened in the past. We're pretty certain where they're going to happen next summer. Let's send the firefighters into the woods now. Let's send them out there in October, November, through the winter, up through March. Cut some fire breaks. Get the woody biomass out of the woods. Combine it with all this plastic we're making, and make some surface fuel rather than continuing to dig the fossil fuels out of the ground. It's sitting right there. It's a liability, and turn that into an asset. So, long answer to your question, but it's basically turning this other forest waste into an energy asset. So
we can use other waste wood materials that would otherwise go into like a landfill.
Yeah, other waste wood materials as well. What you want to avoid, and
from regular forestry practices.
Any regular forestry practice, even building waste to a large extent. Particle board, yep. And this stuff is, right now this stuff is being burned in a power plant, an EPA-approved power plant in Wisconsin. And the idea is, how do we now start shipping it to Asia, use it here in state, and make electricity with it rather than drive all over hell and high water with airplanes and helicopters and fire trucks trying to put the dang thing out each summer. Yes?
So what is the problem with this happening? I mean, what's standing in the way?
The main problem that I've sat, and I sat down with Angela Farr in her office at the USDA a few months ago. And a lot of times, if you actually get a federal project approved, and let's say the federal project, I'm going to go in and harvest 100,000 tons. There's actually 150 million tons of dry standing timber in Montana alone right now. 150 million tons. The problem, if you get a contract, with the Fed to go in and cut some of this stuff down, it's now public record because you've got a contract with the federal government, who has to be transparent in their funding, and they say, hey, look, Leighton and his students and Missoula College and the forestry consortia of Montana now are going to go in and try to solve some of this problem. Well, that becomes public record, and then you'll have someone, and a name did come up, someone like a James Taylor, who has his own financial and political backing. He says, no, you're not going to go into the woods and screw the place up and cut down a bunch of trees and make a bunch of erosion, et cetera, et cetera. You got to keep nature intact, and then the project dies. That's typically one of the biggest roadblocks. You also have a lot of the U.S. Forest Service is a subdivision of the USDA, United States Department of Agriculture, and it's a political organization too, and you've got people within that organization with different agendas too. Some say, no, you got to leave that there. Those trees are going to turn into soil eventually, and we have a soil deficit in this country. Let's leave those trees in the forest, let them turn to compost eventually and turn into soil, rather than getting equipment in there and causing soil erosion. So you have internal politics at the USDA that kills it too. Does that answer your question? Yeah. So again, there's no one answer, but from what I've seen, the best use of these LDPEs and HDPEs is a waste to energy, and the best technology I've seen so far is combining them with otherwise woody biomass waste, something that's sitting out there in the forest as a liability. Let's turn it into an alternative to petroleum-based energy. Yeah.
But it wouldn't be, like you said, that there were landowners.
Yeah.
Do they have the rights to those?
Oh, absolutely. Yeah. If you're a private landowner, yep.
So, but that still wouldn't be enough to like start anything.
Oh no, it's enough. It's enough. Yeah. In fact, Patrick has been working primarily in Helena. In Helena, the private land ownership percentage is about 80%. Around Missoula, it's more like 20%. So if you do have a private landowner, and and you work out the economics and say, hey, I'm going to make enough money selling these energetic products, I'll give you a discount, so you're not going to pay a full forest remediation fee like somebody else might. Yeah.
Because wouldn't that then, then if they came in and did the actual study of the ground afterwards and had data,
oh yeah,
they can prove.
Oh yeah. Oh, we have plenty of data. In fact, just while we're on the topic, I'll show you an example of some.
Because I think, like you said, those trees do not last until they erode into soil.
Rarely, yeah.
And cause more destruction.
Yeah.
Like Brian said, it's not a healthy, it's not a cleansing.
No.
Unfortunately, we stopped the fires for so long that there's that buildup.
So here, here's a bit of data. So my friend Craig Thomas was able to go in and do some clearing around some of Teddy Roosevelt's original cabins. These things are over 100 years old, where he did his forest thinning on federal property. I think there was something like 52 cabins, and he was given access to 50 of them. Did his thinning. Those 50 cabins are still there. The 2 cabins where he did not do his thinning are gone. They're floating around in the atmosphere and empty shells as a result of improper forest management. So there's plenty of data. Yeah, we have there's data, there's studies. He's also worked at a place called the Burnt Fork Ranch. That's in here. Based upon the previous successes of Craig Thomas and his team, as shown in Figure 5, as well as the Burnt Fork Ranch, and this has been written up, decades-old documents. We do not foresee any significant risk beyond the current prices of fossil fuels dropping. So again, what's the risk to killing a sustainable energy project? Well, price of fossil fuels dropping is one. And unfortunately, a lot of times it just comes down to bare bones economics. What people are willing to pay for their energy. So then we get into private lands. So is that again? Yeah.
Actually, yeah.
So we're thinking about the whole system and working on it as a system. Okay, I'll take a break here, and then I want to get into a little bit of research, and I'll try to make this as clear as possible. And I also want to reiterate, you know what, I feel like I should just say some like secret code word right now, so that if you didn't listen to this lecture, what's the minute right now? We can do this. We have technology. What is it right now? It's minute 25. So the word I'm going to say right now at minute 25 is orangutan. And so that will be a quiz question. What specific non sequitur word was uttered during lecture 19 at minute 25?
Oh, you just want people to make sure.
Orangutan. Well, no, I'm serious, because I have received emails from students saying like, oh, I've really been trying to avoid watching those lectures. You know, I would really rather spend my time doing something other than listening to the lectures for a course I'm trying to get credit for. Don't say that.
Because I'd rather be in class than listen to it online. That's all.
No, of course, no, and I think that's true. I think that's true of most people. I think most people would actually rather be in a face-to-face lecture. But in today's society, we are moving towards more online delivery content. So, orangutan. All right. So, the point I was trying to make here, and this is the critical point that I actually want to make at the end of this little lecture, is that I would like you, as part of your skill set for NRGY 270, is be able to go out and do a little bit of independent research. So, this is a 200-level course, and, whether or not you're going on for a 4-year degree or an advanced degree doesn't matter, but I think it is important for students in 200-level courses to at least have some research, independent research ability. I spent a little bit of time now just dinking around on YouTube and Wikipedia, but now I'd like to dig down a little deeper into the scientific literature and see if we can't find some actual studies where people looked at the toxicity of PVC. Because PVC does have chlorine in it. Our bodies need chlorine to survive, but in other forms it could be toxic. So let's take a look at that. That's what I want to do in the last half of the lecture. Do you like that, Shelley? Orangutan?
I don't know how to spell orangutan. Okay. You're not going to knock off points we don't know.
Well, let's do that too. Let's do that too. Let's do that too.
Say a big red A. Red area.
I remember it ends in tan. Yeah, I nailed it. I nailed it. It's not spelled how you think. Orangutan. O-R. So write it down. O-R. Here's your chance. Write it down. O-R-A-N. G-U. Doesn't it mean like old man of the woods? Oh, person of the forest. There it is. Person of the forest. Yeah.
I know, aren't they cute?
That's something else.
Look at them.
That is something else. The orangutan. Okay.
Oh.
Thank you for your attention.